My name is Scandalis, and I'm the CTO and the action CEO of a company called moForte. And I want to tell you a little bit about moForte. We create applications currently for mobile devices, but we'll create applications for whatever device makes sense. We create applications that are based on what's called audio modeling technologies, where we're trying to model existing pieces of hardware, existing pieces of software, and even existing physical objects like guitars and things like that. So today I'm going to talk about a topic that is really extremely important to me. I'm very passionate about it. I'm going to talk about physical modeling of musical instruments. And this is an area that I've had the opportunity to work in on and off for the past 20 years. And today I'd like to show you some stuff that we've been working on. I've got a really detailed presentation. I'm not going to go through the whole presentation. I'm just going to hit the high points on the presentation. And at the very end, about half of the slides deal with questions that I'm frequently asked. So I bring them along to prepare answers for those things. And so if you have questions at the end, we can go through those. I may have a slide that speaks to that. Just to kind of start it out, physical modeling, the modeling of real things like instruments or even the human voice goes back almost 1,000 years, and I'm going to show you guys some examples. And where we are today is we're at a place where almost anyone can see what it's like to be Jimi Hendrix just using a handheld device in the palm of your hand. So the way I'm going to cover this is I'm going to go over, oh yeah, this is one thing I forgot to mention. The presentation can be found here. And if you can't find that URL, if you just go to the news section of the moForte website, you'll also find the presentation. So I'm going to go through a brief but not complete history of physical modeling, and then I'm going to do a demonstration of what's currently possible on mobile devices. And I'll tell you, the power of these mobile devices to do signal processing is absolutely amazing. So I'm going to do a demonstration of what's currently possible, and I'm going to do that using some apps that we've developed at moForte. But first I'm going to do a quick demo. This is my phone. I'll flip it around so you can see. Kind of a taste of what you can do. Okay, so let's get into it now. What is physical modeling synthesis? Today, many products that are synthesizers actually use audio recordings. They're collected, and when you trigger a key, you tap a key on a keyboard, the sample or the recording is played back. And that's a very good way to create realistic sounds. And we actually like samples. That's called sampling. We actually like samples a lot. But the challenge with that is that it's not interactive. And so physical modeling is a different approach where you try to analyze the process that's generating the sound. In this case, for the guitar, you analyze how guitar strings generate sound, and I'll talk about that in a little bit of detail. And then any gestures that are used to interact with the real physical system can be mapped to parameters in the model that you create. And you can create this expressive, kind of experience. The thing that you just saw me play, that's very expressive and it's very difficult to do with some sample-based technology. The other thing to say is that physical modeling is actually a collection of techniques. Unlike the folks who work in the graphics domain where polygon pushing is the order of the day, we have a different technique for each sound generation process. And I did a little taxonomy here. Those of us who work in the area of modeling musical instruments, the algorithms tend to bin into these categories. There's chordophones, which are the guitars, and I'll tell you for the guitars, what we're really doing is solving the partial differential equation for the guitar in real time. There's a solution that dates back to 1749 called D'Alembert's solution, which is the basis for this. Would you go ahead?
I'm sorry, you can't do that and not answer a question because I'm
Go
blown away. Who played the notes? Did you play them?
Yeah, this particular app is set up for consumers. So all you have to do is you can either strum this app when the strings are there or you can tap it. And then the accelerometer and the gyros are where all the expression. Right. And what's going on, I mean, we'll talk about the physicality just briefly. What's going on is the accelerometer, one direction is mapped to the pitch bend, which is changing the length of the string. And the other accelerometer is mapped to the distance between the guitar and the amplifier. And when you move back and forth between the guitar and the amplifier with a real guitar, you get nodes and dead zones that cause feedback. It's the same thing. Everything that we do is based on real physicality.
But not with these speakers, right? It's the modeling is.
No, yeah, it's all inside here.
Like,
yeah, the speakers are just reproducing the sound. Okay, thank you. Okay, great. I'll continue. So, go ahead.
Did I understand you correctly? Every note that you play, you are solving a system of differential equations that represent the instrument in which that note is being played?
Yes, that's true, but there are closed form solutions that are computationally easy to solve. This solution called D'Alembert's solution, which I'll bring us to in a little bit. D'Alembert's solution, it dates to 1749, and it basically says that you can do the hairy math to solve the partial differential equation, or you can say it's two traveling waves with the initial pluck shape, and they travel in opposite directions and reflect off the terminations. And you can build a DSP circuit, which I'll show you, which represents that solution. And it's still a solution, and it behaves in exactly the way that a real string does. So, well, let me just continue with this thought here. The modeling areas tend to break down into chordophones or guitars, which we've spent a lot of time at moForte. Aerophones, which are woodwinds. We've done some work with that. We're not ready to release any products in that area. Membranophones, which are drums, very hard to do, but people do model these things. Idiophones, which are malleted instruments. We've got a lot of technology in this area that we're probably going to do something with. Basically, you hit a bell and it rings in a particular way, and it's possible to model that in a very straightforward way. Electrophones, which are things like virtual analog, like classic analog synthesizers. And then game sounds. There's been some work that's been done in game sounds. It's a very complicated area. And the human voice, which is really the hardest area. We're not doing much with the human voice, but the human voice is, in fact, the starting point for modeling. And we'll just go right to the history. The earliest attempts to synthesize a human voice date back to 1,000 years ago. And what's been known for a long time is that the human vocal tract is really like around 7 resonators, a source of hissing, a source of buzzing, a tongue that touches the top of the mouth. And people have tried to build machines that do speaking. And there are records, though no examples of machines that date back to 1,000 years ago. However, there was a real speaking machine made in 1791, and there's a model of it in a museum. And if you get this deck, you can go to the link here and you can hear what it sounds like. And then in 1857, this gentleman, Joseph Faber, made this speaking machine that really could speak. It had an operator, a keyboard, it had buzzes, it had hisses, and a skilled operator could actually make it speak. Now, it's a little creepy that it has that head up there because there's a mouth that was moving around. But this thing was actually able to speak. And when I say that that's a little creepy, that's an uncanny valley. And I'm going to talk about uncanny valleys with respect to modeling. It's always a problem with modeling. If we make our models not sound exactly right, it causes people to not believe in them or to be disturbed by them. So if you move forward to this idea of the vocal tract being a number of resonant cavities, around 1937, Homer Dudley, who was an engineer working at Bell Labs, came up with the idea of taking the machine from 1857 and he was going to realize it with radio tubes. And that's exactly what he did. He realized a bunch of filters, analog, speech, synthesis. And this is actually fun to take a look at what he was able to do. This was shown at the World's Fair.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cord. There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression. Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
Well, you get the idea, is that this was a device using basically filters, analog filters, to synthesize the human voice. If you come forward to 1961, a pair of engineers developed this model called the Kelly-Lochbaum model. It's a vocal tract model. It's also 7 resonators, but you can see it's represented down here with a DSP circuit. And this is actually the very first digital realization of a system to synthesize speech. And you may actually be familiar, and you may have heard about this, but not realize it. Kelly and Lochbaum were friends with Max Matthews, who was worked at Bell Labs at that time. And he said, I'm going to use this to teach it how to sing. That's right. Now, you may not have heard this version, though. Okay, and I'll drop it out of there. So, one of the things about this is that Max was friends with Arthur C. Clarke, and you may be familiar with this version of it.
I'm sorry, Dave. I'm afraid I can't do that.
Okay. So that's a very important historical point in the timeline of this physical modeling technology. So come around 1983, 2 students at Stanford, and you'll see that there's a lot of stuff around Stanford orbiting around this physical modeling area. They discovered this thing they call the self-modifying wavetable. And this is the famous Karplus-Strong algorithm, and this algorithm has been used a lot, and it's really treated as a self-modifying wavetable. And I'll just play a little example. This is the first musical composition that was made with this algorithm. So when David did this composition, what he was really striving for was to use all the various physical parameters. David and the other principal of moForte, Julia Smith, went on to extend the algorithm, and they created something called the extended Karplus-Strong. And that algorithm was a key part of the sound system on the Next machine, and when the Next machine was introduced, this was performed live on the Next machine using physical models. This was the intro music that Steve Jobs used to introduce the machine. So Julius went and extended this algorithm further to something he called digital waveguides, and this is the point that I made before. It's equivalent to D'Alembert's solution for the partial differential equation. That solution dates to 1747. I said 1749. And much of what we do today depends on this. It's a DSP circuit. It's delay lines, it's filters, it's multiplies, but it represents the solution to the string wave equation, and then we've added so many more things to it to represent physicality, and I'll show some of those things in a little bit. Oops. Back to vocal tracks. At Stanford also, one of the students there, graduate students, Perry Cook, was developing singing algorithms based on the Waveguide algorithm, and I'll just play a little example of that. So this is the part where I start to skip through some of this stuff. Somebody was asking me about the Yamaha VL1 synthesizer. Yamaha licensed this technology from Stanford around 1990, and they wound up creating a musical instrument called the VL1, and it was a fantastic musical instrument. It's not sold anymore, but it's sold on eBay still, and there's a group of people. You have one, I have one. There's a group of people who love this instrument, and I'm going to play two things. These are also modeled, and they're very expressive. There's an overblow that you can hear. And the saxophone, to this day, is amazing to me. When you blow into a little breath headset to play this, and when you blow into it, it really overblows and squeaks just like that. So similarly, Korg, another synthesizer manufacturer, was working on similar technology, and they still offer products that use this physical modeling technology. So here's the deal. In 1994, everybody thought that this was what's going to happen. The world looked like, in 1994, there was a thing called FM synthesis, which was used on sound cards, on PCs, and memory was expensive, and people thought that modeling was going to be the way that all sounds were going to be made for music and synthesizers moving forward. And Keyboard Player magazine really embraced this with 2 articles in 1994. However, and also Stanford invested in this project to try to create a complete musical set using physical modeling. However, what happened is that the value, the cost, the price of memory dropped enormously very quickly, and it became very cheap to just record musical instruments and use those. And so where we are today, now 20 years later, is that virtually every musical system that is a synthesizer that you hear today uses samples if it's playing back real instruments. And samples are great. We like samples. But what's lost with that is expressivity. And people have tried to do things to bring expressivity to it. But with a physical model, you actually get physical parameters that you can control, and it sounds very realistic. So I'm going to skip over a lot of this stuff, but what was done at Stanford was to create this complete general MIDI set. I mentioned to someone here that the team at Stanford built this farm of 8 DSPs to be able to realize the models. And this is one thing I want to go over, is that this electric guitar, the guitar that you heard me play a little while ago, is a direct descendant of this guitar model that was done back in 1996. And actually, I'll play this model from 1996. So if you do happen to download the deck, there's a lot of sound examples in here. I think the most interesting ones are the things having to do with the guitar, but there's also a lot of percussion stuff that's very interesting as well. And this whole area of model percussion is yet to be revisited. No samples, no recordings, it was all just modeled. That was modeled using this technology called coupled mode synthesis, another algorithm developed by Scott Van Dyne. Really fantastic algorithm. You can just take a recording of a percussion instrument like a bell or something like that. You can take that recording and run it through MATLAB, and you get just a couple little filter coefficients to represent the instrument, and it sounds just like the instrument. Another very important area is that there were no virtual analog synthesizers until roughly around this period of time. leading up to 1983, most synthesizers had been analog, and they had this kind of wow, wow sound that we all became familiar with. Then we lost that sound for about 10 years. And one of the graduate students at Stanford played a big role in figuring out how to model those virtual analog things. I actually have a good example of that here.
What we have here is a Synth Builder and Synth Core from around 2000 running on my legacy Windows 98 machine. I've got a patch I've been running on it. It's one of Tim Stilson's Moog VCF patches. I did oscillators in it. I'm going to play it just so you can hear it.
It's a very classic sound. Skip over that. So there was a product in 1997 called Reality that had physical modeling in it as well. And there was a chip that was designed between 1995 and 1997 that used physical modeling technology. However, it was never used for the purpose of creating music. And then there was a company called Staccato that attempted to commercialize the physical modeling technology, and as with many startup companies, wound up doing something totally different, which was to replace one of the hardware chips, the wavetable sound chip that was on PCs. That was a very good thing for them to do. And then here are some game physical models. I think the most interesting one here is this race car, and this was actually used in this game NASCAR 2000. It's a very interactive model. You could step on it, it had hysteresis, you could hear the muffler. You can hear it putter as it comes down. So here's another very interesting area. I said it all started from vocal synthesis. Yamaha has invested significantly in vocal synthesis in Japanese and Japan, and they've started to work on it in the US. And this is a nice example. I'll try to go in the middle of it. This is all computed, synthesized. So you get the idea here, is that even the human voice can be synthesized. And then a company called Smule, who they've mostly been working in the area of consumer music applications, but they did do a musical instrument, a violin. And it's kind of interesting. I think they've discontinued this product, but they wound up getting a real string quartet to use it and actually perform a string quartet. They're holding it like a real violin. Okay, well with that, we'll move on to the next slide. So how's this done? There's a lot of signal processing that goes into this, and there's one of the business partners from moForte has actually written this long book on how to do physical modeling, and it is really a tome on signal processing. In the old days, signal processing was often done in assembly code, and then C and then C++. We're actually not doing any of those things. We write all of our signal processing in a very high-level language called Faust. And this has been a huge advantage because we can build things very quickly. This language is an expression language, so when I write something like a delay line and and a gain and a feedback loop. I can do that all in one equation on a line of code. And so the much of the signal processing that we write, we do in this fast language, and it's also got a very rich prototyping environment. So I can literally write out an equation for what I think is a digital signal processing idea. I can hit a button, and boom, I've got an app on my iPhone, and I can try it out within moments. And so this has been a real advantage, and this is where a lot of folks are spending time doing their signal processing development these days. Okay, I'll skip over that one. Okay, great. So I wanted to move into what's possible. I have I want to talk briefly about the moForte stack. We have a stack, a software stack, which represents the model of the guitar, and we build apps on top of that stack, and we have a number of apps that are built on top of that stack, and that's roughly what the stack looks like. And there's a number of the apps that are built on top of that. I wanted to point out just a couple things about that. There's a demo reel here that you can take a look at if you want to. I'm going to skip over most of this stuff. Yes, I want to talk about the uncanny valley. So one of the things that we've noticed is if the performance of one of these physical models is repetitive, it's identical every time, you get this sense of repetitive mechanical performance. And so one of the things that we worry about is suspending disbelief. And I have a very sensitive ear to the guitar, so I tend to say either that doesn't sound like a guitar, or if it does fool me, it does sound like a guitar. And there's one example that I wanted to play, which is right here. We have built into the stack, into the system, even though it's a guitar and there's places where it's being stimulated, there's the velocity for how it's being stimulated, there's the rate of decay of the elements in it, there's the place on the string where you hit it. All those elements, we've tied those to statistical parameters. So when it's being performed, it actually is not being performed in the same way every time. It's being performed statistically. So if a particular controller, like the pick position, is set to a quarter of the length of the string, it's actually in a Gaussian distribution, and we can set the width of that distribution. And so this particular example shows that. This one fools me. I think I've got a real guitar playing with it. That's very different than if a computer were just strumming it back and forth. Okay, and part of what makes that possible is that, there we go, is that there is a model for the signal processing which represents the guitar. It's actually the model of the guitar. It's where we're solving the differential equations. And there's also a performance model which models how a guitar player plays. And so to that end, we have a big part of the system is built around trying to model how guitar players play the guitar. Okay, I'm going to skip all the way forward to this. So we have another app that's coming out that has some very interesting properties to it. It's really intended for soloists to be able to perform. And I just want to play one demo out of that. And this will be the last demo that I play, but this really gives you a sense for what's possible. Let me back to okay.
So can you program that grid the way you like it?
To some degree, yes.
Because that makes it modal.
Yeah, it is. Yeah, it is a isomorphic keyboard, so you can find lots of different ways to play chords. I'm going to play one more demo here. So one of the ideas is that for this particular thing, we want it to be much more than a guitar, and so it's possible to when you play a solo line to use all 6 strings simultaneously in your solo line. So it's like you have a big 6-string guitar, and I'm going to play this last little example, and then from there I'm going to go into questions. That doesn't sound a lot like a guitar, even though it's based on a guitar. Okay, that's good. Okay. Okay, there is a video gallery if you want to look at any of these videos. There's some interesting videos here. And at this point, I'd like to open it up to any questions you might have. I have a lot of slides that speak to questions that I typically get. Go ahead.
On that last question, obviously you've got spaces for the chromatic scale, so I presume that you can basically select which one of those are enabled to get different modes?
So it's laid out in force. It's actually like a guitar or like a bass guitar. And then you can program which keys are visible by a particular scale or key.
Yeah, I'm referring to horizontally.
Horizontally, it's just always chromatic.
Right, but you've enabled C and D, but you've left out C sharp.
Let me show you the app. That's using, there's some properties of this. There we go. Let's bring up the app. That's a subsection of the screen. So it turns out that there's a property in here called octave rounding. So you can actually, we talk about, we tend to set it up in this mode, which is the whole range of the instrument, but we often play it in a mode where you just have a thing called a magic octave, which is like this, and like that. So you don't have access to that other key, but you actually do through octave rounding because of the way it behaves. So I'm only hitting 3 keys and I'm going up and down 10 octaves. And that's one of the unusual properties of this isomorphic keyboard. That's a whole topic unto its own to talk about. It's kind of and I can talk with you afterwards if you want to, about the isomorphic keyboard and its properties. It has a lot of interesting properties that make it possible to even play on an iPhone and to play very quickly on an iPhone.
Yeah, I guess I'm asking, you can get C sharp if you want it.
Okay, so you want to see the C sharp lit up. You can actually play the C sharp, yes.
Oh, I see. Okay.
So the notes that are lit up is just to help you.
Well, it's a guide, I got you.
It's a guide, yeah.
But you could actually use that as a rule to enforce certain modalities.
We've talked about that, making it so that the keys that are not in the key that you're in are not functional. If that were the case, you could literally just move your hands anywhere and everything would be in tune. And we've met with some opposition for that idea from the musicians in our team. I like the idea.
Well, I don't know who your musicians are, but frankly, you take a balafone or something, you take a pentatonic folk instrument that doesn't have all the notes. I mean, it limits what you can play. So,
right.
And if, we're not trying to do Guitar Hero here. It's not like you just press a fret and you get something, but just as an instrument, to be able to control the modes you might want to play in certain, situations, that's actually pretty helpful.
I believe that making the black keys not play a sound is going to happen. Yeah, I think it's going to be an option because it opens up an opportunity for people who are not that musical to play the instrument. I think that's just going to happen. Go ahead. Question.
Have you tried to create instruments that don't exist?
That what?
That don't exist in real life.
Well, that's, so that's actually what this is right here. This,
like, for example, you create a string that has a tension that's not possible in the real guitar, or something that creates some new interesting opportunities for musicians, because simulating existing instruments, probably it's not that exciting.
So some of the voices that are built into it are actually non-existent instruments, and you can make it's not the physical parameters that go into the model are not things like tension. We actually start from spectra, and that's a whole other topic. We have a way of calibrating it based on spectra, and so but we do have instruments in here which are not like this. Instruments which actually don't exist at all. They're a sort of fusion of synthesizers and guitar. It's actually 6 strings being played simultaneously, feeding back through 6 amplifiers, and then generating this sort of this harmonic texture that you could never get in real life.
That's the overhead.
It sounds like it, but it's not an oscillator. It's a string. Yeah. Oh, go ahead.
Is there a drawing test or maybe Eric Clapton test about distinguishing this from a real guitar pick?
I didn't quite understand.
The equivalent of the Turing test, or maybe if
and Clapton. That's an interesting point. Well, I personally, because I worry about the product, there's a PAT test where if I listen to it, I'll just say that we just can't let that get out the door because it doesn't sound real. And there's been a lot of things that we have just not made available in the product because it just doesn't sound very good. We had a sitar for a while, and we just couldn't get it to sound realistic. It just sounded like a computer-generated kind of thing. So I think that the test is that in our team we have some musicians on the other side of the team who are users, and if they don't like it, that's our equivalent of a Turing test. Yeah. And there's go ahead here.
There are many questions. Thank you. This is brilliant. I think when you try to reproduce an instrument, some things are easier than others. Like for example, the buttons and the notes, right? But how about the resolution of different? Like for example, the distance, the amp distance. Like in real life, you have a few feet or something, so you can adjust it. But there you just have a few, like a very small angle to adjust it. So how easy is to play it from that point of view, right?
Well, let me show you an example of that first.
In other words, how do you solve that problem?
We're using floating point numbers for one thing. So we have a lot of resolution. And so amplifier distance, you asked about that a second ago. I'm going to actually find... so this particular sound... I'm finding those points in the amplifier distance where it drops into a resonant node. And it turns out there's enough resolution in the floating point. Now, this little screen that you see here only has 128 points on it.
I'm not concerned about the floating point, about the distance on the screen, right? I'm talking about, right? In other words, how much do you need to move, or how much space you have to move there to...
Well, the screen is, so, okay, that's a good point, is the screen actually doesn't have very high resolution. So every point that we grab on a screen, we're interpolating. We're actually using our audio signal processing skills to process the graphics as well. So it turns out that every time you move your finger on a string, it's running through a type of FIR filter, which is smoothing it out. Because there, in fact, in this little screen here, it's 128 by 128. There's not enough room in that to find those resonant points where the model actually goes from 0 to 20 feet for the amplifier distance. And so if you divide that into 128 points, you're going to miss a lot of resonant points. Well, we use an FIR to smooth out the points that come from the screen. And then it just happens to be fortuitous that once it starts to resonate, it drops into it. So as you pass your finger from one point to another, you're sweeping through the floating point space of all possible points. And when you find that resonant point, it just drops into it because it gets into this self-resonant system.
And about the modeling part, if I understand correctly, so pretty much you take an instrument, you run it through some kind of some analyzer, right, to extract the frequencies, and then you try to reproduce them with a DSP or what?
That's roughly it. So if you were to take a recording of any guitar note, one of the features of the guitar notes is they decay exponentially in time. You pluck them and they decay exponentially in time. And another property is that the high frequencies decay faster than the low frequencies. And that's actually what makes it sound like a pluck. And what we do is we take a recording of every note for every fret for every string on a particular guitar, and we have some MATLAB code that we run through, and we analyze the spectra, how all the harmonics in the spectra move in time, their decay rates in time, and we design a filter that is inside the apparatus. I'll show you the apparatus here. The particular algorithm is, in its simplest form, there we go. It's a delay line and a filter that degrades the sound as it goes around the delay line every time. You fill the delay line with one period of the sound of the guitar, the first period if you like, that's a good starting point. And every time it circulates, it loses a little bit of energy. If you didn't have this filter right here, it would just be beep, it would just ring on forever. But this little filter here, that's the magic. And so we have an elaborate process for taking all these recordings, crunching on them, and designing filters for every fret, for every string. And so in fact, an instrument in our world is it's an XML file which contains filter coefficients for every fret, for every string, for each instrument.
And that's based for each frequency, or do you have the one filter per string per note?
Yes, for every. So we interpolate between frets. So the frets are essentially diatonic, and when you pitch bend from one to the other, we don't change the filter coefficient. And in the real guitar, it's kind of that way too, because when you hit it down on a particular fret and then bend it up, it really is starting from the properties of that fret that you hit it at.
My understanding was that modeling of guitar is much more complicated than that, because this thing on the guitar, it's not just filter. It affects the string like the string affects back the thing, and it's all like a self-feedback system, right? So it cannot be modeled just with taking the...
That's absolutely true. Well, first off, but there's a handful of features that are the guitar. There's the string itself. There's the pickups. If there is a body, like an acoustic guitar, the body plays a role, and what you would typically do is you generate the sound of the string, and you'd run it through a big, huge filter, which represents the body, and you'd spend a lot of compute on that. In fact, you wouldn't be able to compute that filter in real time. It would not be possible. Because the system is linear and time invariant, you can take the impulse response of that filter, which represents the body of a nice acoustic guitar or ukulele. I get asked about ukuleles all the time. You can take the impulse response and you can use it as the excitation for the string. You're commuting them. And that way you don't have to calculate the filter, which is the body. And so, well, essentially a lot of what we're doing is we're pre-computing those other portions of the system, and we're running them into the string itself. And it's the same as if you ran the string into that complicated filter which represents the body.
How about effect of one string on another?
We do have coupling, and actually the strings are coupled together. The way the model is set up is there's a bridge, and they're trading a small amount of energy through the bridge. So the bridge termination is actually loose in the model. And there's a couple other features too that we're not modeling right today because we don't have enough compute, but it turns out that when a string vibrates in front of a pickup, if it vibrated up and down, that would be, you know, what's going on with the string. But the truth is you pluck it from the side and it vibrates like this, and your pickup is looking up like this. And so we call it a Z and an X component of the motion. And it turns out they're actually at different frequencies, and they couple with each other and they trade energy. And so the way we model that is with two strings, one represents the X, one represents the Z, and we allow them to trade energy back and forth, and they wind up creating this interesting swirly swooshing over the top of the string. Now we don't have that turned on in this version of the software. We're waiting for the next generation of iPads to turn that on. That stuff is actually all in the model, and some of it's essentially turned off because we have computational constraints that we have to work with.
So do you do sympathetic vibrations?
Yeah, that's what's going on between the strings. They're vibrating sympathetically. If we...
Not necessarily with the bridge, but just acoustically, right? I mean, the vibration would excite the other string without the bridge.
Well, it winds up being a lumped impedance that trades between all of the strings. Go ahead.
I mean, it's musical, right? It's almost too musical. The musicality is just beyond belief, right? And so is it because you are modeling one string, one note at a time? Versus, I mean, it doesn't, for example, I don't know if you model anything about what the palm is doing, or the other side of the palm is doing. And if, in fact, when you were strumming, that strumming piece, the decay seemed a little artificial because it was, so is that in there yet, or we don't have the compute to do that just yet?
No, that's there. Let's see. Let me find an example. We wanted to put the palm muting under the control of the user. Where is that? I'm looking for an example. So we've given the user a control where they can do the palm muting. It's a special control that's right here. And then there's over 40 parameters in the system. So this expression pad can be used to control various parameters. It happens to be set up for pitch bend and amplifier distance in this particular patch, but in this one it's set up to be feedback and amp distance. So it's really up to the discretion of the sound designer for what they do with this expression pad. And you can put, it's not that you can put two parameters, one on X, one on Y, you can put a stack of parameters. So you could put a whole bunch of things on the X direction of the expression pad and a whole bunch of things on the Y direction. And then further, we also allow you to use the Y button for expression as well. So there's lots of opportunities for expression, and these particular aspects of the guitar can be mapped into the various expression parameters that are available on the surface so that you can actually interact with them. Yeah. Go ahead.
Switch gears a little bit. You said there's some more challenges with trying to synthesize in human voice while you're talking or singing. You want to elaborate a little bit on that, some of those challenges?
Well, it's a whole field unto its own, and we haven't approached that. And there are many researchers who work in that field, and I think that they, from what I understand, because I'm not an expert in vocal synthesis, I think a lot of what they're trying to do is to model specific human voices so that it sounds like a woman or it sounds like a man, and so they're concerned with the placement of formants. It turns out there's a lot of data around how particular people sound, and so they try to model those kinds of formants. I know that there are folks who have actually tried to take recorded conversations of people speaking and use those to extract data in real time and drive a model as a way of compressing telephone conversations. And that was a big area of research at Bell Labs during the 50s and the 60s. But I don't know much more about that. Vocal synthesis is a whole region unto its own.
Because even when you hear voices, like on Bart or Light Wheel, they seem sort of childish or artificial.
Yeah, and Siri still, Siri doesn't sound very good to me as well. I hear lots of little artifacts in sort of grainy artifacts in the way that it's being produced.
If you were going to model something like klezmer clarinet, so you've got, along with the regular notes, you've got vibrato, you've got squawks, you've got glides. A lot of this is done with the mouth and the breath. So how would that change your modeling approach from all the stuff with the guitar? So people have actually tried to model that, and this particular model, the Waveguide model is what's used for that. We're not approaching that right now. Yamaha worked on that a bit. So what you wind up doing is it's sort of a hybrid between a musical model and a vocal track model, because the embouchure plays a big role. There's a resonance that's happening up there. The bore has its own particular set of things, and then the reed has its own particular set of things. If you listen to that saxophone model that Yamaha did, they definitely have figured out how to use a single valued variable, a slider if you will, to represent turbulence. So that reed, I'll go back to the saxophone and let you hear the saxophone. When you blow hard on this, the reed hits a termination, and it squeaks and squawks.
And I know they're modeling the embouchure, the mouth part of it. There was a squeak.
You don't have a whole lot of parameters though. You just have, you say you can capture it in just a few parameters?
Well, that's the goal with every model, is to try to reduce it to a small number of parameters. And then you build the model to represent the physical thing. So a lot of what we're building in our models are terminations and scattering junctions. And I'm going to just show you a brief example here. I didn't bring this up, but let's see. So I'm going to bring that up. So the guitar model itself, and that's very different than the woodwind models, but let me pull up a particular example here. Demos. So when you strum it close to the bridge, so we're actually, the delay line that we have represents the length of the string. We're actually, we split it where you're plucking, and it naturally falls out of, this comb filter effect naturally falls out of it. And we took it upon ourselves to model harmonics. That comes from introducing a scattering junction into the delay line at a particular point, a nodal point, which is either 1/3 of the way or 1/2 of the way, 1/4 of the way. So that's what I mean by physicality. And we really try to design these systems so that they represent the minimum set of things around the actual physical system, and then we can introduce single-valued parameters to try to introduce expressivity in the same way that the real instrument behaves. Yeah. Go ahead.
And you skip back your sort of Moore's law computing performance over time. How has that constrained physical modeling in the past, and where we are now? Are you hitting that constraint, and where's the opportunities?
Let me actually bring up that slide. I skipped over that slide, and
in other words, what are current devices keeping you from doing, and what do you foresee being able to do with even more power?
Okay, that's a good question. So there we go. So I've been keeping track of these models for about over 20 years, 23 years, how much compute it's been taking us to run these. And on the next machine, which had a DSP on it, you could run 6 of these simple plucks, and you can run 2 to 4 of these guitar strings. And then these are the 2 devices that we built, the Frankenstein and the Cocktail Frank. We were actually able to run whole small orchestral groups, because there were 8 DSPs, and then we pulled the crystals out of the DSPs and double clocked them to try to get more power out of them. So if you move forward here, when we got to a staccato in 1999, we actually were able to run the whole guitar on a Pentium using 80% of the Pentium. And let me tell you, that's not a commercial opportunity. And we used to do these great demos where we would demo the guitar, and there was just not a place for it in that company. There wasn't a place for it in the commercial world. And so that guitar just basically sat on ice for 18 years until we came back to it. On the iPhone 4S, which is our minimum platform right now, we're actually using up about 40% of the CPU to do 6 strings. And that's, you're chewing up everything. You can barely use GarageBand to record with it at the same time. But you can do, and that device is almost gone at this point. I think there's only like 6% of devices installed with that device at this point. The iPad 2 Air, which I'm using about 22% of the CPU for my guitar. Lots of headroom there. We're starting to talk about other instruments, adding other instruments to having an ensemble. We're probably going to add a wavetable synthesizer so that you can have backing tracks, or just the ability to play backing tracks, so that you can really scream your lead on top of that. As time goes on, I don't know what's going to happen when we run out of gas with Moore's law, but we certainly are able to take our model and partition it up amongst cores. There's nothing that would stop us from doing that. And so now you can have one core running a string with X and Y and termination, and we'll use shared memory to throw the sympathetic resonances across the bridge. So I think we're going to keep looking for clever ways to keep moving forward, and our ultimate goal is to expand the number of instruments.
20% of one of the CPUs or 22% of all three?
No, that's just one core. We're just using one core right now. Because that's an interesting point. I told you that we use Faust, this high-level expression language, to generate the DSP. It generates C++. We're at the point now where if we were in a slightly better financial situation, we would hire some additional folks that would just simply take the reference designs we have in Faust and re-implement them in C. And then along the way, we would vectorize them as well. And I should say, back in the staccato days, we actually did, with Katmai, vectorize the DSP, and it did make a big difference. And so it's an opportunity. I'll ask him over here.
Are you doing anything with multiple iPhones communicating with one another?
Well, thank you. Yes. That's one of my FAQ questions, to see if we can find that. I'll just explain what it is if I can't find it easily. So, well, let's see, is it right here? There, wireless synchronized performances, virtual orchestras. Yeah, we actually have a bit of code that's in the system that is certainly not available commercially. We essentially implemented in the musical context, a version of NTP, the network time protocol. And what it means is we can have one device be the conductor, and all the other devices get a signal from the conductor to progress to their next node, and they can be performers. However, they would skew, and in fact, when we first started playing with this, you'd get skew all over the place. And so there's this magic trick in NTP to make sure that the server in Australia and the server in San Francisco have exactly the same time. We just borrowed the same trick. And so it's possible to have a conductor conduct a number of devices. We can put devices on chairs all throughout this room, and they'll all be in sync with each other, and there'll be very little skew between the devices. And a bit of time has been spent on that. We'll probably commercialize that at some point, but right now there's no reason to really commercialize it. Go ahead.
I just wanted to say one of the problems with the human voice is a string, so it has all the harmonics, but it's really got multiple filters. And so it's really like a string played through multiple wah-wah pedals. And there are some of the earlier modeling techniques, like the linear predictive coding, which is an attempt to reduce the amount of information needed to reproduce the voice, characterizes the transitions between the center frequencies of the different filters, of the 2 or 3 filters that the mouth uses when it shapes essentially the single pitch of the vocal cord. And the inflections are called prosodies, and those give the meaning for when you lower your pitch, you go into, for example, a hypothetical expression, and you change your pitch. Mm-hmm. That also gives human speech, the communication. Those are the varieties of things that are needed to make it sound real.
I think there's still research that needs to be done. And I think what you're saying about about LPCs or about a variety of wah-wah pedals. A lot of people use 7. They say that it's like 7 resonant filters, and it's like 7 wah-wah pedals and then you got to find a way to control those. And when we saw the woman at the World's Fair with the stenographer keyboard, she had 7 little things that she was trying to do patterns on to replicate what the human voice does. And if you go back to this machine back here, it's the same thing. They're using these pedals to try to move a leather bag and form it into these various different shapes.
Well, and she was changing the pitch and the inflection, so she was using prosodies. That's what her left-hand keyboard was actually. That's what gave the emphasis to the me or the me, and those were the prosodies involved. Yeah. Just that, right.
Yeah, it's amazing that this was done in 1939. I still am blown away every time I look at this video. Go ahead.
As you said, most synthesis is now sampled. And, for a while, there was something called FM synthesis. I know the Yamaha
still
used that a lot.
Still is, yeah.
So yeah, but you didn't mention that. So I was wondering if nobody used that, or what were the limitations, and why people don't use that.
Well, FM was developed here at Stanford as well. Dr. John Chowning, and then Yamaha also commercialized that prior to the physical modeling synthesis. And one of the initial challenges with FM synthesis is you basically had a handful of just little parameters, the gains and the frequencies of these oscillators, and usually no more than 6 or 7 oscillators. But then the question became, how do you make that sound like a piano? How do you make that sound like a bell? How do you make it sound like things? And early on, people didn't know how to calibrate it effectively to make it sound like things. Later on, I think Yamaha developed some software, and it's a very mathematical topic on how to calibrate that. FM is still around, but it could never approach the level of expressivity or the level of reproduction that was coming from samples. And samples are good. I mean, like, there are some sampled pianos out there that for every possible volume level, for every key, there's a separate sample, and maybe there's 5 samples, and maybe it cycles through those samples. And there are some sample-based pianos that I cannot tell are real pianos. I mean, it's really good technology. You'd never be able to reach that with FM. FM kind of had a level of problems that it could solve, and then it couldn't go beyond that.
But FM, speaking of instruments that don't exist, gives you sounds that don't exist.
Oh, yeah.
And the nice thing about FM is that it's, speaking of reducing the parameters, when you have the frequency modulation, you've got your carrier and your signal that are intermultiple to each other. They create harmonic sidebands in a Bessel function. And just by changing one index, which is modulation index, you change the shape of the envelope structure in nonlinear ways. So that's actually what gave it the natural sounding attack that it had. So it's still pretty impressive.
Yeah, it's pretty amazing. And the other fact about FM is, leading up till 1990, most video games used an FM chipset to make music, because it was very, very inexpensive to do that. And it wasn't possible to do wavetable on a computer up until around maybe 1994, 95. And so FM became really a big part of video game technology. And what's interesting is the students over at Karma now, they were all raised on video games. And the students that I knew 20 years ago are trying to make these amazing morphing, swooshing sounds. And the students now are trying to make game sounds. They revel in making these kind of tweaky game sounds. So, there's still a whole generation that really like that kind of music.
So I think we're sort of dancing around the question. Some people think that we should use synthesis to make new and better sounds, and some people think we should be trying to make better imitations of existing sounds. And it seems like what you're doing is sort of in the middle, because an electric guitar is already not an acoustical sound per se. So where do you land on that?
Quite honestly, our mission is to bring expressivity to players. And particular keyboard players have a hard time getting their head around electric guitar, and I can give them GeoShred, and in a few minutes they can be playing things that sound like an electric guitar player. So that's really what the opportunity is. It's about expressivity. And quite honestly, I think we should be doing, with the stuff that we're doing, we should be doing new types of instruments that people have never heard before. It's a slippery slope to try to perfectly emulate every instrument that's out there. There's always going to be someone who experiences that uncanny valley where they go, well, that doesn't sound like a classical guitar to me. And it's really a very difficult task to meet those expectations. So we say that it's a guitar and beyond, and we're trying to create things that are much beyond the guitar and expressive as well.
Speaking of not doing instruments, you didn't mention brass. Is that easy or not? Just
I don't have a brass sample in there, but Yamaha did that on the VL1 too. I think there's some really good brass stuff out there. The VL1 I think did a trumpet, and you could ping it, and it would kind of do that ping resonance that the trumpet would do. But the thing that happened with the VL1, because they really took it upon themselves to, this is the same topic we were talking about a moment ago, they tried to make it sound like real instruments, and they did a couple larger than life instruments, but musicians became frustrated with the fact that it didn't sound exactly like that instrument, and there was limited expressivity. They couldn't get to in order to make the instrument performable, they had to limit the expressivity, and then they kind of wound up in a weird place with that. And we suffer from that too, because with the GeoShred program, it's possible to play it in a way that it sounds really bad. And just by slamming your fingers down it, you actually have to play it with some degree of skill. And when I'm moving my finger around, finding those feedback points, if I just move my finger around, wave it around, I'm not going to find anything. There's actually some skill that goes into that. And we made the decision that we're going to focus on the musician who can actually enjoy and appreciate that, because that's where the opportunity is with the stuff that we have.
You seem to be steering, so at least at this point, clear off this sort of branded, stack of musical, sort of gadgets, if you will. So like a Les Paul played through a Marshall JCM, that stuff, right?
We're steering clear of it for branding reasons. There's actually, like the wah-wah pedal that I played a minute ago is a real crybaby wah-wah. Okay, so. It's my crybaby wah-wah.
And so you sample it, but you don't, obviously the license.
We analyze it actually. So in the case of the crybaby, we put put an impulse response, and we put a chirp into it, and we looked at how it responded, and we said, okay, we're going to build some filters that match that. And we also have, we call it the classic and the retro distortion, but it's really an MXR distortion plus. It's exactly that. Julius took the circuit and wrote down the circuit as a DSP circuit, and the distortion retro is a tube screamer, and it's exactly that. Again, Julius took the circuit diagram with this funny little diode that has this funny behavior, and he wrote down a DSP circuit that matched it, and we started playing through it, and darn if it didn't sound like a tube screamer. I recognized it. And the MXR Distortion Plus, I recognized it. But we don't call it that for licensing reasons. There may be a point in time when we do arrangements with those companies and license that stuff. But right now, we're just a 2.2-person company, and so we're just trying to avoid any trouble. We don't want any trouble.
but you emulate the circuit inside, the analog circuit that's inside?
Yeah, you can find circuit diagrams all over the internet, like for the distortion. So I'll tell you, the MXR Distortion Plus is literally a 741, and you can go and find the transfer diagrams for the 741. They're all over the place. It's an op-amp, 741 op-amp, and you can create a wave digital filter. It's a particular type of technology that you define it in terms of the filter response, and then there's a magic transformation that's done to invert it, and you wind up with a DSP circuit that does exactly the same thing as the 741 when it's being driven into saturation.
So the soldering and all that stuff is not yet, but this part is there.
Yeah. And there are, we're not the only ones doing this. There are a lot of really smart DSP people who are modeling classic audio processing units. It's a big area, and there's a lot of smart people doing it. Yeah. Go.
So what's your experience with introducing this to students early on or trying different instruments?
That's a good question. So for us, my daughter actually can play Purple Haze on, we've got a game version of this, and but we have, at the present time, we haven't approached education, and there's some very specific reasons for that. Is that, and we're often approached, especially by funders, that say, well, can you turn this into a thing for education? There's a lot of money in it. That's what these guys, the venture capitalists, are thinking. There's a lot of money in it. The problem is we know a lot of people who've tried to do education software, and we don't know anybody who's succeeding. And in my opinion, if you were to take a proven teaching system and translate that into an app, I think you stand a chance of success. But what most companies do is they say, let's make an app to teach people to play the guitar. I think I'm going to think of a way to teach people to play the guitar. And there's no research behind that. There's no educational endorsement of that. And so inevitably those attempts don't do very well from what I can tell. And we know these people in Finland who made this wonderful robot-based video game program that tries to teach you how to play the guitar. And I played with it a little bit, and it was kind of okay, but as a guitar player, it wasn't reaching me. And I know that they have had some challenges with that as well. They just haven't been able to reach their audience. So the answer to your question is we're currently not focusing on education. Though my daughter, I bring her in to play Purple Haze on it, and she does pretty well.
I think this is somehow related to what you were doing before. I think that if you look at the movement space, right, from the guitar versus this, right? So this is a virtualized translation of the movement space from the guitar side, right? So, and you have some mappings, and you have the resolution from one to another. So I think it's quite challenging to actually do that. So I really don't know why would you want to do that. I think this is a really awesome instrument. Just make it like a virtual instrument that happens to sound like a guitar, but hey, like crazy with it.
That's essentially the pivot we made last October. We said because as I said a moment ago, there's ways to play it so that it sounds really bad. It's because the physicality, the real instrument is there. And you can play a real guitar badly as well. And so we said, look, we have this great technology, and when we show it to people, they get excited, especially musicians. So let's focus on those people who can get excited about it.
Yeah, the converse of that is also true, is that it takes a while to learn how to play a real guitar. It takes time, it takes practice. I think there's a whole generation of people out there now that pick up an iPad and go, I'm gonna play guitar, and go, and it sounds terrible.
Yeah.
Because they don't have that practice ethic. They don't have the ability to sit down with this. Now, if you take a look at some of the people that do that, like our friend Jordan, or somebody who can actually sit down and practice with an iPad and practice with a piece of software and learn that as an instrument, that's going to take a fair amount of time. And there's so much, instant gratification now that people pick it up, play with, oh, this doesn't sound good, and they'll throw it away. And they won't spend the time to learn that as a new instrument. So the same thing happened with synthesizers when they first came out, right? Switched on Bach came out, everybody said, I can do that, and then Switched on Country came out. And
it's going to make it so that I can play music.
It's terrible, right?
Yeah.
So, it does require, these are new instruments. And I think that not a lot of people really get that.
Well, I think the financing community, from the financing people that I speak to, have been perpetrating a myth, which is now it's going to be easier for people to play if they just get one of these things. And it's not. And the truth is, so when I recorded the Freebird thing this morning, I spent a day practicing that. And the reason I spent a day practicing it is because I got it up in capo and I transcribed it and I wanted to see exactly where all the wiggles were. And in order to suspend my sense of disbelief, to get past the uncanny valley, I had to figure out how the original player played it exactly. And there was a day and a half of figuring that out. It wasn't I'll sit down in front of an iPad and all of a sudden I'm going to be the Leonard Skinner's guitar player.
And it was a day and a half for, I assume, a pretty good guitar player, right?
Yeah, but it's a new instrument to me.
No, but you have all that meta information.
That's true, but even if I played it on the guitar, I still would have had to do the same thing. Because I would have had to listen to it and go, oh, when he goes back on this note, he wiggles it for a while, and then he goes all the way from the bottom up to here. I mean, there's...
The point is you have that experience of the actual guitar to be able to translate that.
Right.
You even know what that with vibrato, like wiggling
and other people may not have that experience.
You don't just put on a pair of skis and go down the black slope.
That's right.
That's what people expect.
Well, but that's their problem.
From the sound, you have to reverse engineer what the person did, and then have the computer do the opposite of that, right?
Yeah, that's right. Yeah. So for people who are musicians who cop licks, a lot of the work is about reverse engineering what the original player did, and there's a huge amount of subtlety to that. And there's actually a program now called Capo that allows you, it brings up a spectrum and it helps you use the spectrum to try to figure out what the original player did. How hard did they hit the notes? Where did they wiggle it? Did they do a slide? And all those nuances come out of that kind of thing. But it is a reverse engineering problem, and it takes a skilled musician.
More money in that than forward modeling.
Yeah.
So have you thought about other? I mean, you've got the technology for the model. I talked before about other controllers. Have you thought about applying this to other surfaces or other types of instruments that, like the hang drum or something that it's a spatial type of thing that could be sensed with in some way to drive the algorithms in a more natural way?
Well, that's a two-part answer. One is if it's coming from MIDI, we're going to release a version of it, and we'll have a way to customize presets for specific controllers, like unusual controllers like the jam stick, like the moth band, the instrument. If it's coming from another device that actually has analog signals, that's actually very interesting. But there's not very many people making those devices right now. And the idea of a hand drum that has some analog signals that we can bring in and use them concurrently with the trigger signals of now play a note, that's a very interesting proposition. I think somebody's going to have to build one of those.